conservation of momentum. So first, conservation is not a concept that is new to you. When we talk about things being conserved, what is the case? What has to be true? When we talk about conservation of something, it has to stay the same, right? So, by definition, conservation of momentum would look like this, right? Sigma pi equals sigma pf. First, what did the sigma represent? The net or the summation, the sum, right? So if we do sigma pi, p representing momentum, right? Sigma pi means the total initial momentum, or the net initial momentum, has to be equal to the net final momentum. Does that make sense? So this is how conservation of momentum is defined. But what does that look like in reality? Let's take a look at this picture. All right, here, cue ball, 3 ball. We've all probably seen this, right? That if you hit the cue ball just right into the 3 ball, you can make the cue ball stop and the 3 ball moves off on its own, yes? Okay. So, at the beginning, the top part of this picture this part of that picture, I'm not sure why that big black line's there, but go with it. The top part of this picture, this represents the initial condition, yes? Before the two of them run into each other. Cue ball is moving. Does it have momentum? Yes, it does. 3 ball is moving. Does it have momentum? Or sorry, 3 ball is sitting still. Does it have momentum? Momentum depends on 2 things, right? If we calculate the momentum of an object, we take its mass, multiply it by its velocity. Does the 3 have velocity right now? No. It does not. So does the 3 have any momentum to begin with? No, it doesn't. So if we're looking at, right, the total initial momentum, we take the momentum of the cue ball, add it together with the momentum of the 3 ball. Yes? After the interaction, right? Cue ball stops. 3 ball starts moving. Does the cue ball have momentum afterwards? After the interaction? It does not. Does the 3? It does. So, if we're looking at the total final momentum, all of the initial momentum was contained in the cue ball. All of the final momentum is contained in the 3 ball. What does that mean about how they're moving? It would be the same what? On one condition, right? Like, what would have to be true if they were moving at the same speed? They would have to have the same mass. Because it's not speed or velocity that is conserved, it's momentum that is conserved. Okay, go ahead.
I just have a random question.
Good.
But saying that they weigh the same, is that wrong or right?
If they're on Earth, saying that they weigh the same is okay. Remember, weight being the force of gravity, right? So if they have the same mass, they would have the same weight. Okay? I always try to make sure that I put it in terms of mass, because that's really when we talk about the amount of mass, the matter that's there. I always try to say it that way. But saying that they weigh the same is okay, because technically that would be true if they have the same mass. Although here, you know, you would say the velocity would be the same if they had the same weight. Weight really isn't in this equation. It's more mass that's in that equation. So to be technical about it, we should probably go mass. All right. So they would move the same if they had the same mass. Technically they don't. The cue ball is a little bit heavier than all the rest of the balls on the table. A little bit, but not much. So, but if that's the case, right, if the cue ball is heavier, what would we say about the 3 ball after the cue ball ran into it? How fast would it be going? It would actually be going faster than the cue ball was going, because it has to make up the difference in the mass. Good there for starters? Okay. All right. Let's take a look at this picture, not that picture. picture? Ah, striped girl and blue girl, they're back. Okay. So, striped girl pushes on blue girl. We've already established that we know this happens. Is momentum conserved in this picture?
No, well,
The answer probably should be what? If this is a slideshow about conservation of momentum, what should the answer to this question probably be? Yes, right? But if we look at the beginning, how much momentum do they have together? None. Right? But what are they both doing here? They're both moving, so they both have momentum now. But the answer is yes, because of one of our questions when we were text polling yesterday. What do we know about momentum? What kind of a quantity is momentum? It's a vector quantity, right? So the answer is yes, due to the vector nature of momentum. If we look at the beginning, right? We've already established initial velocities for both girls are what? 0. So their total initial momentum is then 0, right? So the total initial momentum has to be equal to 0. Okay? But striped girl pushes on blue girl. Blue girl feels a force, but striped girl automatically feels a force back. So they start moving in opposite directions. When we go to calculate their momentum, one has a positive velocity and one has a negative velocity. Will these two girls move at the same rate? Will they have the same speed? If their mass is the same, yeah. But I would say probably here that striped girl looks to be a little bit bigger than blue girl. So if striped girl is bigger than blue girl, striped girl's velocity would be smaller than blue girl's velocity. Does that make sense? But when you go to calculate their momentums, because one has a positive velocity and one has a negative velocity, then you go to add them up, right? What are you going to end up with? If you add a negative number plus a positive number that are the same, you end up with 0, right? Now remember, it's the momentum that is the same. The product of the mass and velocity, not just the velocity. Good there? Okay. Why does this turn out to be the case? So let's take this picture here of striped girl and blue girl and pop it here in this. Okay. All right. First, does blue girl experience a change in momentum? Yes. Meaning that we can apply this equation to blue girl, right? Impulse momentum, just like we talked about. Let's say striped girl pushes on blue girl with a force of 10 newtons. And let's say, for argument's sake, that that push lasts for half of a second. Okay? Then, I don't know, blue girl has a mass of 60 kilograms, and we can figure out what her change in velocity is. Good there? Okay. But, does striped girl experience a change in velocity, or a change in momentum? Yeah, she was not moving, now she is moving. She had 0 momentum, now she has momentum. So, let's see if this works. Too big stuff. I changed it before, but I'm wasting valuable time. It's okay. All right. That equation applies to striped girl as well, yes? Because she experiences a change in momentum as well. What do we know about the force that striped girl experiences? It's the same, but negative. So really here, this is negative 10 newtons. Here's the important part, though. If striped girl pushed on blue girl for 0.5 seconds, how long did blue girl push on striped girl? 0.5 seconds. It's a contact force, right? That means they can only apply forces to each other if they're in contact. if that's the case, here and here, force and time for striped girl, force and time for blue girl. These are the what's for striped girl and blue girl. They're the same. What term are these? What do we call the force times the time? That's the impulse. Okay? But if they have the same impulse, what else do they have? The same change in momentum. But, Roxanne, do they have the same impulse? No. Why not? One's positive and one's negative. So one's momentum becomes more positive, the other one's momentum becomes more negative, but the end result is what? They're the same, or 0. Right? All right, we'll finish this up tomorrow. Hey, don't forget, beginning of class tomorrow, before we get into lab, you have your first quiz over this section. It's just over the impulse momentum equation, not over conservation stuff that we did today. So notes from Monday, concepts from Tuesday, lab stuff,